job in uh, in setting this all up for us. This is a series of symposiums that NGDI has been doing. We had one last fall around COVID-19 and vaccine development. We had the great honor of having outstanding speakers for that session, including Dr. Peter Cullis that Dr. Hancock got us, who is, as you know, the inventor of the lipid nanoparticle that was used in the delivery system of the Pfizer vaccine for COVID-19. And so in our continuing way of highlighting the importance of global health, neglected disease research, and bring you awareness of what NGDI UBC is all about, we're doing a series of these symposiums and seminar series for your enjoyment. And today we have an outstanding set of speakers and panels that my colleague, Dr. Lester, will talk about in big picture in a couple of moments. But what I want to do is kind of give you a little bit introduction to the Neglected Global Diseases Initiative and who we are, and what have we been up to over the last number of years. So NGDI UBC was actually initially founded back in 2010 by Dr. Hancock, myself, but really a village of individuals. There was amazing colleagues, faculty members, graduate students, summer students, undergraduate students, other scientists, upper administration, and so on, that came together for a common mission and common cause. And that was founded on the idea that what we learned was that UBC had a rich history and rich experience in neglected global diseases. And back in 2010, at that time, President Toop and the VP of Research, John Hepburn, had provided Bob and I some initial funds to do an environmental scan across the UBC campus to find out, are there people doing research and doing activities, doing education, doing advocacy in this area. And, you know, the joke that I make to people all across campus is there are neglected people doing neglected disease research all across this amazing campus, at our affiliated campuses, and now subsequently at the UBC Okanagan. And but they needed a home. They needed a place so that they could do their research. They needed a place for advocacy. They needed a place so they could PR their work. They needed a place so we could help them facilitate their work, help them get funding so they can continue their outstanding work, get them with partners and people around the world so that they can bring their work to real life practical situations. And so that was why NGDI was started back in 2010. And really over the last decade, we've been able to help facilitate a number of people's research. We've been able to highlight their great work. But most importantly, we've been able to help them connect with the key partners around the globe that they could work with so they could bring their work to fruition. And if you go to our website, which we are now updating, you can see a lot of the projects that are handling, a lot of the faculty members are doing their work and so on and so forth. And you can see our mission. And our mission was to develop interventions for those in need, you know, and get into them. You know, it's great to do the research at UBC and the UBC family, but if it doesn't get translated onto the ground around the globe to help people with whatever infliction they have, then really it's just an academic exercise. And so we're very proud that we've been able to have many of the folks to been able to translate their work. And you can learn about all the kind of great research people are doing from the website, which is being updated and modified as we speak. The other, I think, important thing is our student engagement. We are very supportive of students in doing research and interventions and activities around neglected global diseases. In fact, we have a very rich student body that are great advocates for NGDI and NGDI UBC research. And we all know as academicians that they are our next generation of scientists and thought leaders in this field. And so giving them an opportunity to be involved in this, I think, is really important. The last 2 points I'll make before I pass it over to my esteemed colleague, Dr. Lester, to talk a little bit about today's symposium and then to start the proceedings is we've got some activities in NGDI. Not only are we doing this new series of seminars over the next little while, we had the one in November, we have the one today, we're going to have one hopefully live in the fall. So just want everyone to know that there is a lot of new activity at NGDI. Second is we've got a refreshed website that we're working on. I just got UBCIT to update it so you can get it on your mobile phone and do a few other things there. But you'll see some new content and some upgrades to the website over the next little while. We're going to be doing an aggressive public relations fundraising campaign starting in April. I'm working with a firm, or we're firming up, the advisory board is firming up a relationship with a firm to start to get PR out about NGDI to the global community and beyond, to everyone around in the world, and also to help us in our ability to fundraise for activities for NGDI. And the other thing I want to announce, and this is directed towardly to students, is we've been able to secure some small funds for a student-led award in NGDI. And hopefully we'll be able to roll that out in the fall. The money has just now come in, and we need to get with our advisory board to set up the terms of reference for this award. And so that will be something that you'll hope to see in the fall of 2022. So lots of great things going on in NGDI. And today is just an example of what we're trying to do for the community. So with that, I will pass it over to Rich to make some comments, and then we will start the proceedings. So Rich, over to you.
Hey, thanks, Keishan, and thanks everyone. I'm really excited about today's lineup. As those of you who may have attended our November session, we were still decided that COVID, we were in the thick of it. I'm not sure where we are now, but it was really important to look at it from a neglected perspective, and we had some amazing scientists. This session today, the last time, a couple of things happened that changed from the focus from our last symposium to this one. One is we're back to, we've got a number of amazing speakers speaking on neglected global diseases and issues that are not COVID today. Not that has gone away from our consciousness completely, but the other is that we realized last time, and it was just by chance, we had a number of speakers. We ended up with four male speakers last time. This time we had a number of speakers. We ended up with 4 women speakers, and it came together right around the time of International Women's Day. So we were quite thrilled to see that balance is brought back to the universe. Hopefully we see that also with COVID and our overall global approaches to getting balance in the work that's being done. And part of that is I'm really excited. 2 of our talks today are related to malaria, which is still one of the really important pathogens that causes a lot of undue deaths, and especially in younger kids. And a lot of work still needs to be done. We're talking about recent breakthroughs, and then sepsis, which in pediatrics, which Dr. Amy Lee will be talking about at the end. Very critical and ongoing important issues. So I'm not going to say much other than we're very honored by our high-level speakers. We've got a few from our first one is from the UK, but also does work in Africa. Second speaker, Jen Gardy, many of you know, was at BC, a BC person and still probably is at heart to some level. We're so thrilled to have her back. And then we also have Dr. Amy Lee over our partner university at SFU, talking some of the great work that's happening there. So I'll pass it on to Dr. Kathryn Pluis, one of our board members, to introduce our first speaker. Thank you very much.
Thanks, Rich, and thanks, Kish. Yeah, it's my absolute pleasure to introduce Professor Kathryn Maitland. She's a professor of Paediatric Tropical Infectious Diseases at Imperial College London, and she's based at the KEMRI Wellcome Trust Research Program in Kilifi, Kenya. She's been based full-time there for the last 22 years and has conducted phenomenal research in pediatric infections, many huge clinical trials in children with life-threatening illnesses. Her group's notable works include the controlled trial of fluid bolus therapy in 3,141 children with shock, that's otherwise known as the FEAST trial, and a second very large transfusion trial in 4,000 children with severe anemia, which is also known as the TRACT trial, and a controlled trial of oxygen therapy in nearly 2,000 hypoxemic children with severe pneumonia, which is also known as the COAST trial. So Professor Maitland's talk today is entitled Out of Africa, the Fluid Bolus Story. And so thanks so very much, Kathryn, for agreeing to speak at our symposium. We're thrilled and excited to hear your talk.
Thank you very much. I'm going to turn my video off, and then I'm going to switch to the sharing my screen, and hopefully all the technology will work. Can everybody see that?
Not yet.
I don't see it.
Nope, there's nothing shown.
Yeah, sorry.
Oh,
Yeah.
Can we
thanks,
give
Jay.
can we give Dr. Maitland share screening capability here?
I think, Dr. Maitland, I think you should be able to share your screen. You have been made co-host.
I know, but
It's
not working. Sorry.
So maybe what we can do is you were kind enough to send us your slides, which is excellent. Maybe Sammy, you can download it on your computer and share, and then we can go that way.
It's not downloaded yet. Okay.
Well, it is. I have it here. Are you comfortable with me sharing the PowerPoint, or
Of course
would you,
I am.
you can try one more time?
Yes, yes,
Oh.
I am.
Thank you. Awesome. There we go.
No, thank you, Kathryn. It's always great to have that backup. So, and to everybody who's on, just keep your microphones mute, and if you want to turn your video off, that would be great as well. Help with our connectivity. Thank you, everyone.
So,
Sorry, the computer is being slow today. Okay, there we go.
I can start to make the presentation, and then we can catch up with the with the audio once we actually get the visual. And thank you very much for inviting me. Yes, I think Kathryn was responsible for me to joining you. We've known each other because we've been trying to do some work in severe malaria, particularly children who have renal impairment with severe malaria. And she's got some fantastic funding to take that forward. So that's just a little bit of background as to how I was invited. Is the screen ready to share, or is it not happening yet? So yeah, there we go. Right. So if I'll be saying next. So hopefully that won't sound too bossy. And so yes. So this is a story that had an unexpected finding as far as all of the trial investigators was concerned. And next slide, please. And as Dr. Pruse has already said, this is about the FEAST trial, which was published now over a decade ago in the New England Journal. So why was the FEAST trial necessary next? So many children who are hospitalized who do end up dying, most of those deaths will occur within the first 24 hours, meaning that the decisions that you make and what you do as you first see that child may be absolutely critical. From our program, we collect lots of clinical data systematically, and we were able to actually look at this and realize that actually 15% of children actually had shock in those who died. And the case fatality was pretty poor. This was before we did the FEAST trial. So we were wondering whether fluid boluses could improve outcome. There's something equivalent to your PALS or APLS, which is emergency triage and treatment. That was about to be imminently rolled out, which would include giving children fluid boluses. But when we talked to doctors, they all said we're a bit worried about this because we're a bit concerned that giving lots of fluid might harm children, but we don't know about the benefits. So the only way to do this is to do a controlled trial next. So we originally, while we were trying to source funding, we actually started to begin to generate the evidence, first of all, about the fact that a lot of children did have shock, and then also undertook some dose finding studies in a whole range of conditions. So we were able to show that fluids corrected shock. We had validated which was the best fluid, but we hadn't conducted a control trial. Next slide. So this was, and everybody said, well, why didn't you have CVP lines in and all of this stuff? Well, you can't do that in a big clinical trial. You'll see the type of conditions that we did this in. So we had done quite a lot of this work before. We were able to look at myocardial function in children and various aspects of hemodynamics in children receiving fluid boluses. And we were able to show that children's heart rate, actually, they were very tachycardic before they got the fluids, but their heart rate reduced, where their CVP actually went into a normal range. And we were also able to show that they actually didn't go into heart failure. Next. And as I say, we were interested in whether there was any benefit from any of the colloids, and we looked at all of the colloids, saline, gelafusin, and albumin and dextran, and we found that actually, when we looked at all of these were all done in malaria, we found that actually albumin had a very good signal for benefit over any other fluid. So we felt that that had to be involved in any future trial. Next slide. So where was the rest of the world when we were trying to sort of think about a controlled trial of fluid boluses next? So the current standard of care or pediatric recommendations at that time was to give up to 60 mils per kilo of fluid boluses to improve perfusion over 15 minutes. And this was included in the Dellinger Surviving Sepsis guidelines in 2020. And let's see where that recommendation came from. Well, it was largely based on next slide, largely based on a single study at a single center that actually did a 10-year review. So that means it's including just over 90 children. So that means only 9 children per year. The patient populations that had to survive to be admitted to ICU. And then they went and they were looking back at how much fluid and how fast they'd been given in the first hour. And they found remarkably that 60 mils per kilo over 15 minutes, and many pediatricians find that incredibly difficult to give, but these were community physicians. Well, they found that that provided early shock improvement and in 34 children, and then that became the standard of care for the rest of the world. So that was a weak recommendation based on a very, very poor evidence, and that was the evidence before for pediatrics worldwide. So next slide. So we had a lot of challenges trying to get funding for this, because there was a very strong view that you shouldn't be giving extra fluids, particularly in children with malaria. Pediatricians said, we know the fluid boluses work, therefore it's ethical to have a control arm. And we also had lots and lots of challenges in terms of how we were going to get the sickest children into this trial, those who probably would benefit the most from fluid boluses. And so we had to sort of formulate ways of doing that. Of course, issues over blinding. It's very, very difficult to blind a controlled trial. And also there was absolutely no ICU backup these are the realities of the work that we had to conduct. Next slide. So finally, after many years of applying for funds, we got the FEAST trial was funded. Next slide. And we wanted it to be a pragmatic trial. You get a critically sick child appearing in the emergency room. You don't know what the diagnosis is when you want to give those fluids. So we tried to have relatively minimal exclusion criteria. We didn't want to include gastroenteritis because that needed a new protocol in itself, and also children with severe malnutrition, because that would have really threatened the approval of the actual ethical approval of the whole trial. So there was relatively few children that were excluded from the trial. Next slide. Just to give you a sort of flavour of where one of the centres that it was conducted in, this is Soroti Hospital, that have over 8,000 paediatric admissions. Next slide. And this is where you would arrive as an emergency. These are the 3 children that have just arrived there in the last half hour. All, as you see, there's nothing that goes beep there. You know, it's very, very, we had to be very practical and pragmatic about the way that we conducted the trial. Next slide. So we've got the funding, and then I've now had to, there's no off-the-shelf demonstration of how you're going to run this great big huge 3,000 patient trial. So we had to we had many challenges operationalizing this into a reality. Next slide. It was hard. It was a really uphill struggle, but we had to think very, very hard, and we had to, next slide, be very creative. Like many things in Africa, we have to have solutions where you might not need solutions for other things. Next slide. So first of all, we absolutely worked within good clinical practice guidelines. We ensured that all of the teams were trained. We did a dedicated GCP course for all of the study staff, so they actually understood the context of how to do good a clinical trial. Many of the doctors and nurses had never actually done research, let alone a large phase 3 clinical trial. We developed an emergency consent process, which we've published, allowing the sickest children into the trial, and then subsequently getting approval. We ran, rather than this being run from London, this was all run from Kilifi in Kenya. We had an open source software which was actually FDA approved for the data management, and we had full-time monitors on this trial, so every single piece of documentation, 100% source document verification. And we our serious adverse events were monitored real time, and we provided quarterly summaries to the ethics boards. Next slide. So this is where we managed it from. This team is larger than my original team, but these were all of the people who helped run the FEAST trial. Next slide. And I'm very proud that the issue of female and leadership has been brought up, because this was a trial that was absolutely very, very much driven by many very, very, very talented females. And obviously our statistician, Babika, was one of the world's best statisticians. We were very lucky to have him on board. But yes, there's a lot of girl power there. Next slide. So what was the design for children who had febrile illness? We wanted for them to be, they had to be sick. So they had to have an altered consciousness and or respiratory distress. Often that respiratory distress is acidosis. That's why they're panting. So we got the sickest children, and they had to have at least one sign of impaired perfusion. Most children received 20 mils per kilo. We had a protocol amendment towards the end of the trial enrollment to increase that to 40 mils per kilo, but most kids just received 20 mils per kilo. They were allowed a second bolus at 1 hour if you were if your shock had not reversed. Then we had the control arm who received maintenance only. They were only allowed to receive a bolus if they dropped their blood pressure. Next slide. So training was really important. everybody got trained, and not just once. It was it happened throughout the trial, so people could actually stick to the actual ensuring that they enrolled the right patients, ensuring that they followed the protocol, and they just felt part of a team. If that we had quite a lot of oversight. We actively solicited adverse events. We were trying to look for fluid overload events, looking for anybody who people suspected had pulmonary edema, had a neurological deterioration. Next slide. So we provided infrastructural support. Next slide. This was one of the places that we got, and so there wasn't any provision for oxygen. There was one tank in the middle of the hospital, so we actually brought in oxygen concentrators to make sure that all children got all of the other additional aspects of care. So the only thing that varied between children was that what they were randomized to. So they got antibiotics, oxygen if they needed it, all of those other things, but the randomization arms were the things that varied between the children. Next slide. Primary endpoint, well, you couldn't really argue with 48 hours mortality, and again we had very robust secondary endpoints, but we also were concerned about any adverse events, and that included neurological deficit, but also we were, as I said, we were looking for fluid overload events, and all of these events were actually monitored by an endpoint review committee. Next slide. So we were absolutely enrolling very, very quickly. There's actually 3 lines, and you can see that they're all overlapping. There's no deviation, meaning that absolutely everybody was following their randomization. And then almost 2 calendar years after we started, we were asked, I got a telephone call. Next slide. As I said, it was going smoothly, and next slide. And this was after the 5th interim analysis. This is the IDMC, you might call it DSMB, that's the Data Monitoring Committee. This is the only committee that ever got to see the data by arm. As trial investigators, we're never allowed to get any data summaries, and the database would know that we'd gone in there and tried to actually look at that. So these were the only people that actually knew the accumulating mortality, or the accumulating sort of comparison between the arms. And they've after nearly 3,000 patients have been enrolled, and the chair of the committee said fluid boluses can be of no benefit to African children. And I was absolutely bowled over, because we were trying to look for adverse events, and we weren't really seeing that many. And they were a very strong recommendation that the trial steering committee was to actually advise both the funders and the sponsors to stop enrollment into the trial, which has actually happened the following day. Next slide. So this is what the data monitoring committee were actually seeing. They started off that they've done, as I say, they did 5 interim analyses, and you see this is what's called a forest plot for people who are not familiar. If on the left-hand side, if fluid boluses was a benefit, then you would see that the spot, or usually the triangle, would be on that side. And you see that they gradually, as more and more children were enrolled into the trial, the truth became apparent that actually fluid boluses, as you see on the right hand side, increased the risk of dying or were harmful. Next slide. So this was the actual result. Fluid boluses actually in both the albumin arm and the saline arm, we're on the wrong slide, sorry, were harmful. Yeah, harmful. We're going a bit too fast. Thank you, that's lovely. And again, so although albumin and saline have different properties, you can see, you can almost superimpose their effect on mortality in the both bolus arms, and compared to no bolus, that obviously was significantly worse. So that was the primary endpoint, 48 hours. But what about the secondary endpoints? Next slide. So again, there was no catch up by day 28. Boluses still were harmful compared to no bolus strategy. So again, this was looking like a very robust result. Next slide. Just coming back to these adverse events, we're asking everybody to report anything that they thought was harmful. And remember, we've got over 3,000 children, and you see the relatively few events that were actually reported. And this was then looked at blind to actually which intervention arm were by the endpoint review committee, and they found that actually there were probably unlikely to be related on the majority of them. So there was only 3 were probable in the bolus arm, albumin bolus arm, and 1 in the no bolus arm. So there was yes, as I say, it was we weren't seeing excess fluid overload events. Next slide. So we were able to very luckily get this into the New England Journal. It was a fast track review, and we were still rather traumatized by the result, because we still couldn't get our head around why this had happened. Next. And we had a mixed response. There was a lot of people just said this was amazing, and there's a lot of people that just said you had the wrong children in the trial and you harmed them, and they hadn't actually really read the actual details of the thing. But I think that we felt very reassured about the quality of our data. It got into the New England Journal, but also we were awarded the paper of the year by the BMJ annual awards. Next slide. So what had happened, and obviously the first thing that we went to see whether there was any systematic methodological blunder. Next slide. And so this is what, as our statistician Abhijit would say, that these are the 4 R's of a successful trial. The first one is, did people successfully randomize and follow that randomization? Well, that was 100%. So you couldn't argue that there was any weakness there. In terms of children who being eligible for the trial recruitment, we only had 2 minor violations. Remember, this is over 3,000 kids. Adherence, everybody stuck to the randomizations. So there was no actual faulting for that. And in terms of the primary endpoint, we were almost 100% complete in terms of that. So again, this didn't seem that we had run a bad trial. Next slide. But the other thing that was absolutely consistent, and as the trial statistician said, that never have I seen anything so consistent in my life, that actually every single pre-specified subgroup, there was everything as to the right of the line saying boluses increase risk. So there was no single subgroup in which we could find that there was any benefit. And we've done subsequent. Next slide. We've done lots of subsequent looking at things, which I'm going to present a bit later. But one of the things that we were strongly criticised for, that we should have only looked at children who had WHO shock. Well, we looked at all of the shock definitions, and for each single one, particularly the WHO one, that fluid boluses were worse than the control arm. Next slide. So yes, as I say, I was going to talk about subgroups. Next slide. And certainly people were more interested. They said, well, this is just a malaria slide. Well, if you give fluid boluses to kids with malaria, no, it wasn't just a malaria slide. We did have quite a lot of children with sepsis. Those who had a sepsis definition, again, fluid boluses were harmful compared to no fluid boluses. And particularly, yeah, we've got, not all of the sites could do blood cultures, but even in those that did have a positive blood culture, we see exactly the same trend. It's all in the same direction. Next slide. Was it because all of our kids were anemic? Well, we had hemoglobins across the whole range. Yes, we did have children who were severely anemic. And this is, again, another forest plot. Control is better if it's on the right-hand side. Bolus is better on the left-hand side. And again, we see that irrespective of your hemoglobin level, fluid boluses are harmful, even into the normal range. Next slide. So what did explain the excess mortality? And this was, as I say, we had pre-specified endpoints, and the endpoint committee decided what the mode of death was, which was very well structured. Next slide. First of all, we were able to look at, did fluid boluses actually improve reverse shock? Well, fluid boluses did improve shock statistically better at 1 hour, next slide, compared to no bolus. But actually shock reversal did not protect children. Actually, there was no apparent benefit from shock reversal by bolus compared to no bolus. They still had a higher mortality. Next slide. So the actual cause of death, this was a cardiovascular, basically collapse. The endpoint review committee was kept on looking at these children and thought, God, these children should have had a bolus of fluid, thinking that they were scoring the fact that they were actually, they died in unresuscitatable shock. But actually this was happening in the bolus arm compared to the no bolus arm. So children and doctors from the bedside, when we actually saw them, they said, oh crikey, they're shocked, they reverse shocked, they woke up, they got better, and then an hour or two later they got pulled back to the bed and the child had collapsed and they couldn't resuscitate it. So this was the main cause of excess mortality. We'd got neurological events and also respiratory events that we pre-specified the criteria, and again we saw no difference in those two. So that was the predominant cause, was because they went back into unresuscitatable shock. Next slide. So we've actually looked at how harmful was fluid boluses. How long did the effect of harm occur? This is not a nice slide. The next one please, sorry, next slide. But actually all the way out to 96 hours after a fluid bolus did we see excess mortality. So if I just reminding everybody that the vast majority of children only received 20 mils per kilo, which some of the investigators thought was almost homeopathic. But there we are, that's what we'd shown. But it's, you know, the fact that they can actually still have an effect on mortality quite a long time downstream. Next slide. So this reminds everybody that fluid's a drug, and it's you have to be very careful about not thinking it's just the miracle cure, and that you have to think about dose and how fast you give it, etc. Next slide. And since this was published, that there has been a very, very nice critique of bolus resuscitation and where did all the evidence come from. And there's, I can remember people saying, well, there's a lot of mouse model work and there's this, that, and the other. Actually, the evidence behind it was very poor. The vast majority of what's emerged into guidelines has been based on expert review. So I strongly recommend, if anybody's interested, this review of where fluid bolus resuscitation came from. Next slide. This was another paper showing almost identical sort of, if you give more aggressive fluid resuscitation, you have almost the same increased risk that we saw in the FEAST trial in those who were given by protocol more fluid than who were given obviously a lot less fluid. This was a trial in Zambia. People could pulled holes in it saying, well, there's too many patients with HIV, but still it delivered another result suggesting that aggressive fluid fluid management was harmful. Next slide. And really, I think this, the timing obviously of the FEAST trial was also timed at the time when people were beginning to be concerned about positive fluid balance and the fact that actually there was association with increased mortality that went just beyond, obviously, the sickest patients get more fluid. And so that it was really at that cusp that people were thinking, hang on a minute, do we need to rethink our practice? And I think a lot of people, next slide, have. This was a fluid bolus study, which I actually did the editorial for. Again, they showed that there was no difference between a restricted fluid bolus in the control arm compared to standard of care. But what they also found was actually that the paediatricians were very reluctant to actually follow standard of care. They were more wanting to. So they actually had a lot of protocol deviations that people were, as I say, much more concerned about fluid overload and the harms of fluid by the time this study had been conducted in the UK. And next slide, and I'm just going to go through a series of now study protocols that are widely available of people around the world also beginning to look at these. So as I say, that we can just run through the next few ones just to give you all of the examples of what's happening. Next slide, and then next slide again. These are all protocols, but also people have looked at whether the feasibility of also doing this. Next slide. And they found that it is feasible, it can be done, and that we're now waiting for the results. And I think the classic trial is about to be published. But let's see. I think next slide. And again, this just a lot of now sort of where the whole field has moved around fluid resuscitation and people wanting to have a lot earlier wind down or even a less aggressive starting point. Next slide. Oh, there's more. As I say, it's just that there's more layers and layers. And I think this is my final slide. Next one. Yes. So we were the first because we had to do it. We had to show that fluid boluses could save lives before it could be absolutely and utterly rolled out in Africa, and we proved that it didn't. We were also able to show the mechanism for that, but I think that it was at a point when more people were getting concerned about the volumes of fluid that they were giving and the potential effect on patients. And thank you very much for listening.
Thank you very much, Kathryn. That was excellent. Sorry, your last slide got a bit cut off there.
It doesn't matter.
It's okay. All right. Thanks again. It was a phenomenal study and subsequent body of work that followed into, fairly, like you were saying, a fairly unexpected outcome. And so, yeah, I think there's probably a lot of questions from the audience. I guess people can speak up directly if they have a question.
I think Bob had his hand up. Bob?
No, I was applauding. Interesting, very interesting talk.
Well, even sorry about the I could be running it myself.
Yeah. So Kathryn, Kishore was on. We've met through email. Thank you very much for an outstanding talk and really excellent story. Maybe I missed it, but could you talk about the composition of the fluid infusions that are used, and what kind of compositional changes could influence some of the effects that you're seeing? And I'm talking about concentrations and proteins, lipoproteins, lipids, things like that are used in fluid retention.
Oh, crikey, that you've caught me off guard on that one. So the fluids that we used were provided by Baxter. They
Okay.
donated they donated the fluids, and we had to store them in accordance to their guideline, which is
So they
tough.
were standard normal saline, different types of fluids that Baxter provided, right?
They were, yes, and so just to ensure that there's no conflict of interest there, Baxter donated the trial fluids, but they weren't involved in any of the design, running, interpretation. They got to hear the results about 48 hours before the paper. So they were, as I say, they were high grade solutions, and we had to keep them in the conditions that they were. We have to obviously store everything below 30 degrees, and we had to ensure that. But it's quite interesting because we actually stress tested the albumin. We thought, well, if albumin is going to save lives, everybody's going to say, well, how can we sort of store this? So not for the stuff that we used in the trial, but we left it on shelves in the bright sunlight. We took it around in vehicles that end up, sitting out in the sun, that end up at 50 degrees, and then we sent it to Baxter in Germany, and they said, well, why are we testing this fluid, because it's absolutely fine. So albumin is a very robust product, but we weren't able to show that.
Yeah, my apologies for the question. What I was driving at is I used to work in a previous life as an ICU clinical pharmacist, and we used to do IV infusions for fluid recitation back in the day. And we would have the standard IV bag, normal saline 5%, 10%, D5W, and so on. But we would also inject into the IV bag, increased concentrations of plasma proteins or increased concentrations of normal saline, and then infuse that into our patient to help with the resuscitation process. And I was just curious if there had been studies looking at those different, when you change the components within the fluid, did you see different effects on these patients?
So we didn't do that, and I don't know whether anybody else has. I mean, people have beginning now to look at different types of crystalloids, obviously plasma light, etc., and that trial has been published and haven't really shown any benefit. But in terms of actually adding things into the resuscitation fluids, we didn't do that. They were given separately.
I understand. Okay,
so
great.
There was no contamination potentially of those
Sure.
fluids. We were very mindful of that.
Okay, great. Thank you. Kathryn, I think there are some other questions in the chat for Dr. Maitland.
Yeah, we have a question from Dr. Anthony Chow, the previous head of adult infectious diseases. His question is, what is the current recommendation regarding fluid therapy and shock?
So there has been a more recent guideline, international guideline. WHO have been very slow to change their recommendations, which was incredibly disappointing. But internationally, there's a recommendation that in resource-poor settings, children should not receive fluid boluses unless they are hypotensive. I didn't talk about that. We had that stratum of children who were hypertensive. They were all meant to actually receive fluid boluses, but the sample size was so small and the mortality was so high that's literally too few patients and too late in their course of illness that, as I say, by the time you become hypotensive, it's really very poor prognosis. Sorry, did I answer the question?
Yes, I think so. Yeah, slow to adopt the findings into.
Yeah, so internationally they've been more adopted. WHO, we had a very good communication policy. We had a strategy. I went straight to Geneva to tell them about this. This is really important. We know you're about to publish your next set of guidelines, and they just ignored it. They just said it's only one trial. But it's like only one trial. Look at the result. Exactly. So we do recommendations for the rest of the world, but they could have had a well, I've actually reviewed their actual review of the feast trial, and they were innumerate. They didn't get the numbers right. They said there was more children that received fluid boluses than that didn't receive it. Therefore, that the investigators got their numbers wrong. You know, and honestly, as I say, that there was nobody with technical statistical competence that actually had written that review of the, you know, their overview of what the results of the feast trial were.
Wow.
And
Well,
it was
good that there's a lot of good supporting evidence subsequently. There's a few questions, hands up. We've got first, I think Rich Lester had his hand up, and then Bob Hancock after Rich.
Thanks, Kathryn. They're really, I mean, important, impactful stuff. And I just think, especially when you're talking about something that takes, you know, it's not a niche drug or a niche treatment. This is sepsis is such a broad-based impact, and one of the most simplest dogma-based approaches that you're influencing, and science is really at its best when it can try to help us dispel myths, understand that better. So amazing work and story. In terms of the underlying causes of sepsis and the effect on boluses, you had a mix. You said some were malaria, some were non-malaria. There might have been also bacterial infections and probably viral infections with subsequent inflammatory responses and sepsis as well. And I know your initial trial wasn't disaggregating those, and you found this remarkable forest plot that put everything into its detrimental category. Is the latest thinking, do you know that the source of sepsis or type of sepsis matters in these sick children?
I mean, this is a conversation that I've had with others around, obviously, those who manage meningococcal shock, and, you know, should they even think about sort of what the feast trial and I just said, no, I think that you can't think that meningococcal shock is the same as, you know, I think that one size doesn't fit all, and we probably didn't have enough children of a specific bacterial etiology to be able to say anything. But overall, when you're deciding to resuscitate a child, you have absolutely no idea what's going to be the end, until we get better diagnostics, I suppose, at point of care. This is the evidence, certainly for Africa, but it is a good point. But we have subsequently refined this, because a lot of children in malarious areas will go to church with malaria parasites. That, you know, if they've got a malaria infection, it doesn't mean that that's caused their current illness. So although we did see quite a lot of those children had a very, very low level of parasitemia, meaning that their cause of illness was something else.
Thank you.
I hope I haven't confused people.
Excellent, thank you.
I think Bob had a question next.
Yeah, so of course it's incredibly disappointing doing a trial where you're hoping to demonstrate a positive effect of a relatively simple treatment. But I'm a great believer in value added. So I'm wondering, when you're doing this trial, did you collect a bunch of other parameters that would allow you to have some insights into why children actually died from sepsis and these other conditions?
So we had very, very, very detailed narratives. When a child died, we had information from all of the baseline data. We had sequential hemodynamics, not CVPs or anything, but heart rate, blood pressure, and we had lactate over time and various other things. And the endpoint review committee would look at all of that information and say, this is how we thought the child had died, i.e., unresuscitated, no pulse, etc. We think this is cardiovascular collapse, we don't believe, or we believe that this is related to the intervention or not. So that's what they were tasked to do. In terms of we've got a biobank from admission, but nothing beyond that. It was just too expensive. We wouldn't have been able to do that. We have some further data. We had some biochemistry at 24 hours, but we'd missed most of the deaths by then. So we don't have any more granularity in terms of additional blood samples to look at.
I guess it's sort of a shame, because this is one of the largest trials I've ever heard of in this, in sepsis-related deaths in infants, which is crying out for information.
Mm-hmm. Well, if you've got any ideas, do email them to me. We'll see if there's anything that we can look at from the biobank from admission. Then we're looking at, we've actually we're hoping to finish, just getting funding for this, looking at markers of myocardial damage, troponins, the natriuretic peptide, just seeing whether there was evidence that they were higher in those who subsequently went on to have harmful effects of fluid.
So have you stored any samples from the patients, like blood, for example?
So we have, yes, we've got a biobank from admission, but nothing from once if they died. No, nothing.
Okay, thank you.
We didn't take any post-mortem stuff, no.
Yeah, it's interesting. Thanks, Bob, for the question. It's interesting, just as you've already mentioned, Kath, how in malaria there's been, sort of the classic approach of, restrictive fluid management is generally the dogma for many, many years. And I mean, the hypothesis there is, it's a microvascular, sequestration of the parasite. And so, despite giving fluids, you're not actually it's not a macrovascular problem, and you're not actually helping severe malaria patients by giving them fluids. And so it just makes me think about, sort of a generalized sort of endothelial problem, even though they're dying from, sort of cardiogenic shock, but whether there's sort of a peripheral aspect of it contributing. Has there been any thoughts to that, or any way that that's been able to be looked into?
So whether there's endothelial damage, not specifically just to malaria, but beyond that, whether fluid bolus has caused that. I mean, obviously we could look at it at admission, but nothing sadly beyond that. So I mean, we had hypothesized that, again, this is based on clinical observational data, that when we actually saw the children, often they came in, they were peripherally shut down, they were very cold, and we resuscitated them. Their thready pulses became bounding. As I say, they woke up, and then they collapsed. And whether we were actually reversing the mechanism that was keeping them alive too fast before we could actually treat their infection. I mean, we hypothesized that, shock might be a good thing. It might be the thing that I know it's associated with poor outcomes, but whether you can get on top of what was causing that before you reverse the shock. That was one of our potential hypotheses. Another one was, actually if you're so shut down and you basically, I think it was one of our collaborators described it as toilet flush, effectively reperfuse all the toxins, and whether that was also quite harmful.
So I think we do need to wrap up this first session. So so thank you both Kathryns for this. Dr. Maitland, thank you so much. And there are other questions, and we will ask. We will see if we can get those submitted to you from our things. And thank you, Kathryn, for leading this session. So why don't we move to our second session? So again, thank you very much, Dr. Maitland. We really appreciate it. And I will turn it over to my esteemed colleague, Bob Hancock, to introduce our second speaker. So Bob, over to you.
Thanks very much, Kish. So I actually have to go off and teach in a minute, but I couldn't resist introducing Jen because of my sort of personal interactions with her in the past. So Jen Gardy, as I think everyone who's probably here knows, is a consummate communicator and broadcaster, a tremendous educator and a heck of a scientist. She basically got a PhD at SFU with Fiona Brinkman. And while she was there, she won the Governor General's Gold Medal and as well as the SFU Outstanding Alumni Award. But she then came and did a postdoc at my lab at the University of British Columbia. And she wasn't a bad postdoc, published 12 papers in 3 years. But the thing that I remember most about Jen was when we went off to a meeting together in London, and I convinced her to ride the tube with me to the hotel from Heathrow to downtown London. And Jen told me about how she'd started to become interested in science communications and that she'd taken a media communications workshop in Banff. And I spent most of the tube visit trying to persuade her that the best science communicators are people who are immersed in science. And I'm really pleased to say that Jen at least spent a lot of her career immersed in science. She then went on to become a senior scientist at BCCDC. And there her best known paper in the New England Journal of Medicine is one of the first papers looking at genomic epidemiology, particularly of tuberculosis in British Columbia. And she also became an associate professor at the School of Public Health. During this time, because she had so much spare time on her hands, she became a frequent blogger, a frequent host of the CBC's Nature of Things, and also wrote a children's book called It's Catching. She then went on to become the deputy director at Bill Gates in the area of surveillance data and epidemiology and global health as part of the malaria team. Jen is a fantastic communicator, and I think we're all looking forward to hearing her today.
Well, thank you, Bob. That's the sweetest introduction. And I'm sure you'll be pleased to know that I still regularly use the tube as my mode of transport from getting from Heathrow to either the Foundation's London offices or wherever else I'm heading. That was super cute. I'm going to talk about what's hot, where it's hot, tools and approaches for malaria eradication. And big high five to Samia, who is going to be handling slide duty for me. If you can flip it around so we get it into full presentation mode, that would be amazing. It's mostly just a bunch of pictures. So as Bob mentioned, I joined the Gates Foundation. It's been a little over 3 years now, and there I'm in charge of the slice of the malaria portfolio related to surveillance data and epidemiology. We basically do 3 things. We focus a lot on strengthening routine surveillance systems for malaria, everything from doing surveillance assessments to just going in and investing in better surveillance systems, period. We've got a big chunk of work devoted to carrying on genomic epidemiology, so using genetics and genomics to interrogate both the malaria parasite and the vector, looking at things like anti-malarial drug resistance, insecticide resistance, population structure and diversity as a surrogate measure for transmission intensity. Lots of cool stuff there. And the third piece of the portfolio is really around supporting geospatial and mathematical modeling to better understand malaria epidemiology. That portfolio is one of several portfolios within the malaria team. If you're at all familiar with how the Gates Foundation works, you'll know that many teams there tend to have a very R&D focus. They're interested in diagnostics, therapeutics, vaccines, things like that. Malaria is sort of unique in that we really have an end-to-end strategy that covers investment in everything from that upstream R&D, your diagnostics, your therapeutics, your vaccines, all the way through to data for decision making, like I support in my portfolio, right through to delivery of interventions. We've got a portfolio that touches on our relationships with entities like WHO, President's Malaria Initiative, the Global Fund, and part of that portfolio also works directly with country programs, National Malaria Control Programs, or NMCP. We've also got a policy advisory and communications team. We've got a new team on digital health for malaria elimination. So we're pretty unique at the foundation in that we really do take a pretty holistic investment approach to looking at the entire malaria ecosystem. So today, with that big picture perspective and the ability to look across all of the things we're investing in at the foundation, not just my little slice of the malaria pie, I thought what I'd do is share some of the really exciting new developments that are happening across the board, whether it's R&D, whether it's delivery, what's hot, where it's hot. And the takeaway message that I hope to leave you with is that I really believe that we can achieve malaria eradication, zero malaria worldwide in our lifetimes. It's going to take using the tools that we have already in a much better and a much smarter way. And it's also, as you're going to see today, take a lot of new innovations, new transformative tools, new approaches. But I really do believe that we can get there, and maybe some of you will play a role in that journey too. Samia, if you can go to the next slide, I will give folks a really quick overview of malaria, although I'm sure it's something that you're probably fairly familiar with. Carried or caused by the Plasmodium genus of parasites, mostly Plasmodium falciparum and vivax, but there's a couple of other little other Plasmodia in there. Those are carried by mosquitoes in the genus Anopheles. There's about 400 Anopheline species out there, and only 30, 40 or so are competent to carry that parasite. So it's a small handful of Anopheles that are actually responsible for transmitting malaria, and which are the dominant vectors is very geography dependent. Malaria, of course, as I'm sure you all know, really does have a disproportionate impact on children as well as pregnant women. With children, it's an immunity issue. They just haven't developed much immunity to the parasite. And with pregnant women, it's sort of a temporary immunosuppression issue, along with some weird parasite biology that means it likes to hang out in the placenta. But disproportionate impact on those two groups. And in total, we're looking at, according to the latest WHO estimates, about 241 million cases a year, 90% of which are concentrated in sub-Saharan Africa. And again, largely concentrated in Africa, over 600,000 deaths estimated to be caused by malaria every year, mostly pediatric. A child does die approximately every minute from what is a preventable and a treatable disease, and that's just not acceptable. Many people don't know that malaria used to be very common around the world. It wasn't actually eliminated in the USA until 1951, and Europe only saw elimination in the 1970s. Elimination, of course, being no local transmission. Your only cases are travel importations. So really in that second half of the 20th century, you saw most of the middle-income countries and high-income countries eliminating or getting very close to elimination. China was, I think, most recently elimination certified by WHO just a couple of years ago. Burden, though, has increasingly concentrated in lower income countries, particularly sub-Saharan Africa. Even in sub-Saharan Africa, though, we have seen progress. If you look back over the, say, year 2000 to 2015, and you look at malaria incidence, whether you're looking at rates or whether you're looking at raw case counts, it really did plummet pretty significantly over that time. And a lot of those declines can be attributed to two vector control interventions: bed nets, sometimes we call these LLINs, long-lasting insecticidal nets, and a second intervention called IRS, or indoor residual spraying, which is spraying a long-lasting insecticide in the interior walls of a home structure. So with those two interventions, plus a couple other things in our toolbox, in that 2000 to 2015 period, we did make remarkable gains in sub-Saharan Africa and other places. We probably saved around 11 million lives, prevented about 2 billion cases. But if you look at that chart, which was down like this for such a long time, around about 2016, 2017, those declines started leveling out. And due to the fact that malaria is concentrated in sub-Saharan Africa, which has a growing population, although malaria incidence rates have been still declining slightly over the last few years, the raw case counts are actually starting to tick up again since you've got a larger population denominator. The WHO in 2015 set out something called the Global Technical Strategy for Malaria, and it set a number of targets to reach by 2030, including a 90% reduction in cases, 90% reduction in deaths, and they wanted to see 35 countries added to the elimination list. And while the elimination agenda is going well, it's actually ahead of our expectations. that burden reduction piece is stalled. We're very, very far behind on progress, and we're not going to achieve those 90% reductions on that 2030 timeframe. And in fact, if you look at modeling, especially some of the work that's come out of that part of the portfolio that I support at the foundation, the modeling shows that if we keep doing what we're doing in terms of a malaria control effort, we are definitely not going to meet those global technical strategy goals. And even if we dramatically ramp up our coverage of our existing interventions, get more bed nets out there, get more seasonal malaria chemo prevention, it's still not going to be enough. And so it's really telling us that we need a new approach to planning for malaria control and elimination, and we really need new tools as well. Happily, though, the community all recognizes the danger that we're in, this precarious situation, and whether it's WHO providing updated guidance and policy, whether it's the Global Fund, making sure we have access to the right commodities that we need, whether it's implementers like President's Malaria Initiative and USAID going out and actually getting interventions into the field, and then donors like us at the foundation, we all as a malaria community recognize that if we want to achieve that dream of eradication in our lifetime, which we all believe is possible, it really is going to take a dramatically new and different approach to malaria control going forward. So Samia, if you can advance to the next slide, I'll just give you quickly a sense of the 5 areas that I want to talk about today, within which there are really cool either new tools or new approaches to addressing malaria. And I think it'll give you a flavor of how it really does take innovation across the board, from research and development all the way through to delivery, if we're going to get over this sort of current stagnation and progress and get ourselves back on track. We'll talk about everything from stratification and subnational tailoring, all the way through to super cool tools in vector control and gender. But if you go to the next slide, we'll start by talking about stratification and subnational tailoring and WHO's HBHI initiative, which stands for High Burden to High Impact. And the headline of this section of the talk is that if we're going to get back on track when it comes to malaria progress, we really need to move away from a model of one-size-fits-all intervention planning to a much more bespoke model. So what you see on this slide here is data from the Malaria Atlas Project showing the incidence of malaria in Burkina Faso 20 years ago on the left and today on the right. And the oranger it is, the redder it is, the more malaria. So if you look at that figure on the left, you'll see that 20 years ago, malaria was fairly evenly distributed across the country. And when malaria is everywhere, doing a one-size-fits-all approach, getting your effective interventions out to as many places as possible is the right thing to do. So what the old approach used to be was get bed nets out to as much of your population as possible. You take the population denominator of your country, divide it by 1.8, order that many nets, and get them out the door. And if you had money left over, you'd go in and do that IRS spraying wherever you could. And like I said, that was great in the 2000 to 2015 period. It really did drive incidence down, and it gives us now what you see on the right. Lower incidence overall, but a much patchier distribution, where particularly in urban centers, those large blue dots reflect some of Burkina's larger cities. Not a lot of malaria in those places, but still you do have high rates of malaria, almost unchanged from 20 years ago, hanging on in this case, some of those border pockets up in the northern border of the country. So this, I'm showing you Burkina Faso, but this is the story all across sub-Saharan Africa. We went from very homogeneously distributed malaria to a much more patchy distribution. And that's reflecting basically different epidemiology in different parts of the country. And what that tells you is that if you want to use your limited malaria control funds more effectively, you should be delivering the right set of interventions to the right places. Different epidemiology is going to require different packages of interventions. So for example, if you're in an urban setting, mosquitoes generally aren't going to enter into urban dwellings. These are, big, nice houses, high rises, things like that are relatively mosquito proof as compared to more sort of rural housing models. So bed nets might not be very useful in an urban center. The money that you're saving by not putting bed nets into a big city could be better deployed, doing a different intervention or doing more bed nets somewhere else where they're really needed. So it's about getting the right interventions to the right places. There's a lot of information that goes into deciding what the right intervention for the right place is. If we just stick to bed nets, for example, you might say, okay, well, that makes sense. Don't put bed nets in cities where there's good housing. Let's focus it on places where that you need that extra physical layer of protection. But then one of the questions could be, okay, well, what's the dominant Anopheles vector in the region that you're talking about? Not every Anopheles likes to bite inside at night. Many of them prefer biting outdoors in the daytime. If your dominant local mosquito vector is an outdoor daytime biter, is a bed net going to do much good? Probably not. So again, don't spend the money on nets there, use different interventions. And similarly, mosquitoes are becoming increasingly resistant to pyrethroid-based insecticides. And that resistance arises in multiple ways. Sometimes it's genetic, sometimes it's metabolic. And depending on which type of resistance it is, what its sort of upstream physiological cause is, sometimes you can overcome that resistance and make pyrethroids effective again by adding a second chemical, something called PBO, onto the nets. So these dual nets that have the pyrethroid and have PBO are much more expensive. But if you're in an area where your mosquitoes are resistant to pyrethroids, but have that special type of resistance that can be overcome with PBO, it makes sense to order those more expensive nets and use them there. So that just kind of gives you a sense for, even for a simple intervention like a bed net, there's a lot of different things that might influence, is that going to be effective in an area or not? So thinking about this in the big picture, 2018, WHO launched the high burden to high impact approach, which was focused on the 10 highest burden countries in sub-Saharan Africa, and really trying to get them to do a 180 in terms of progress and get on track. The centerpiece of HBHI has been what they describe as strategic information to drive response, which is basically a new way of doing your malaria planning. And we also refer to it as stratification and subnational tailoring. So instead of the old way of doing things and saying, let's just get a few interventions out to as many places in Burkina Faso as possible, what you do now, the first step is you sit down and do a stratification. So you divide your country up into typically districts. This might be done at a sub-district level. It could be done at a state or provincial level, divide it up into little chunks. For each chunk, you assign it to one of a few different risk bins. So you might have a bin for districts that are urban settings and very low transmission of malaria. You might have a different bin for forested rural settings that are very high transmission, and so on and so forth. You might have anywhere from sort of 3 to 6 different bins. You've sorted each of your districts in the country into one of those bins. Then you figure out for each of those types of bins, the urban low transmission, the rural high transmission forested location, for each of those different bins, what is the best overall package of interventions to deploy there? So typically an NMCP will develop a few different ideas of intervention packages, typically based on both WHO guidance and whatever commodities are available from the Global Fund, as well as what budget envelope they're being given to work with. From those different scenarios, they'll use modeling approaches, math modeling, to compare which of them will generate the best benefit relative to the others. And typically that plan, that package of interventions, then gets kind of written into stone as the country's official national strategic plan for that type of district. And my work, that I mentioned off the top of the foundation, is really all about creating the data reagents that you need to do this process, the surveillance data, genetic data to tell you about resistance, and the modeling and analytics capacity in those NMCPs in sub-Saharan Africa, in those local universities that they can collaborate with to allow the program to really develop and compare scenarios. HBHI has been going super well. We've done the first round already, and while it's still too early to see results in terms of decreasing incidence, we've seen results in terms of huge excitement around the process. And in addition to those 10 original HBHI countries, 14 more countries in sub-Saharan Africa have signed up to be HBHI settings in the next round. So we're just about to launch the next round of stratification and subnational tailoring work for this expanded geographies. and it's going to be a super exciting time. So this is a really nice example of a new approach to planning for malaria. If we go to the next slide, I'll start to tell you about some new tools. And I'll start in the prevention bin. If you've traveled to a malarious area before, you have probably taken malaria prophylaxis, and you might have wondered to yourself, if I can take a pill to prevent myself from getting malaria while I'm on holiday, why can't everybody take pills all the time to prevent malaria? It'd be completely impractical to take a pill every single day. We can't give Malarone to everybody all the time, but we can be inspired by chemo prevention and do slightly different things that are more feasible for a sub-Saharan African context. The biggest one of those is what we call SMC, or seasonal malaria chemoprevention. This is done in areas where malaria transmission is really packed into just a few months of the year, where it's highly seasonal. And typically malaria transmission season will be 3, 4, maybe 5 months long, depending on the local geography. So what SMC is going out once a month and giving a round of artemisinin combination therapy to children under 5 once a month during transmission season. And typically where it's happening now is in the Sahel region of Africa. 2 exciting things coming down the pipeline for SMC. Number 1 is expanding SMC to new areas. Like I just said, it's typically done just in the Sahel, but doing climate modeling and keeping careful track of malaria incidents has shown that there are some pockets in southeastern Africa, I'm thinking of places like central and northern Mozambique, for example, where malaria is just as seasonal as it is in the Sahel and should be eligible for SMC. So expanding into those new geographies, and there's also some work being done on the benefits that you would get from expanded age range and going up to include either children under 10 or children under 15. The really exciting thing, though, in the SMC space, I think, is the potential for replacing the current version of SMC, which is those 3 rounds of an ACT once a month, replacing it with a single encounter injectable monoclonal antibody. So like I said, SMC is multiple visits. It's a 3-day treatment. The first dose is taken as directly observed therapy. The subsequent 2 are left with the household, and that obviously is going to create adherence issues. And in fact, if you look at what you would have expected from SMC benefits in terms of decreased morbidity and mortality, we haven't seen the magnitude of benefits that we would have expected from SMC, which really does underscore that there is probably a strong issue happening when it comes to adherence and taking those subsequent doses. And sometimes it's just, a challenge issue too. Like, you might not be able to get to a remote community to bring that second round, bring that third round of drugs. So obviously anything that is just a single encounter with the healthcare system is going to be preferable, and we think a single injectable monoclonal is the way to go on this. There's 2 targets that are currently in phase 1 human trials. They both target CSP, which is the circumsporozoite protein on the surface of Plasmodium. This is the target for the RTSS vaccine as well. The results from one of those phase 1 trials are in and have shown 100% efficacy, which is pretty incredible. That particular trial is now in the dose de-escalation phase. And what's very cool is that these monoclonals actually seem affordable enough for widespread pediatric use. And we've got a target of getting them below $10 a dose, and it looks like we'll be able to meet that. The other thing I wanted to quickly mention in prevention, I would be remiss if I didn't talk about RTSS. Exciting news last year, WHO endorsement of the first ever vaccine for malaria, indeed the first ever vaccine for a human parasitic disease. It's exciting, but it is not perfect. If you've done digging into RTSS, you'll know that it's got a not great efficacy. The duration of protection is very short. It is restricted to just the pediatric population. 4 to 5 doses are required. It is very expensive, and there is a very limited supply of both the vaccine and the accompanying adjuvant. And countries right now, as they're doing their stratification and subnational tailoring, are looking hard at, is RTSS something they can even implement? Are the trade-offs against existing very effective interventions like bed nets just too great? So RTSS, it's mixed feelings on that. But what we are really excited about are the 2nd generation vaccine candidates. BioNTech, for example, are pursuing several mRNA vaccine candidates. We at the foundation are providing some support into candidate selection and designing that optimal CSP construct. And the goal is to ultimately find a vaccine that can be greater than 80% effective in both kids and adults. At the same time as we're working with BioNTech on the mRNA vaccines, there's also work on the more traditional subunit vaccines, and can we just improve them? Can we make them better? So instead of the RTSS CSP construct, looking at replacing that with a new construct, R21, as well as testing out some new adjuvants. So some exciting news in the vaccine space. Next slide, we'll go to case management. This one I'll mention really quickly. Case management just refers to diagnosis followed by appropriate treatment. Diagnosis is done with rapid diagnostic tests. Everybody, I'm sure, has probably taken a COVID home test, one of those lateral flow assays. Malaria, same thing, except we use a blood drop instead of a nasal swab. These are easy, they're cheap to do. They've made a huge difference in terms of allowing community healthcare workers to get out there and diagnose cases. The challenge with the current RDTs, though, is that they detect an antigen on the surface of Plasmodium called HRP2/3. And what's happening is that certain Plasmodium species have deleted HRP2/3 out of their genome. And so they can still infect people and cause disease, but it'll show up as a false negative on an RDT. So the current work in this space around improving diagnostics is all about using a new antigen, lactate dehydrogenase, or LDH. So these second generation RDTs are now being rolled out in areas with high HRP2/3 deletion frequencies. So super exciting, that's happening now. A long-term interesting play in the diagnostic space is the notion of doing a non-invasive diagnostic to detect hemazoan crystals. So when a red blood cell is infected with Plasmodium, the Plasmodium causes the production of this substance called hemazoan, which will crystallize. And it turns out that if you take a cell phone, do a little modification to it, shine a red laser from the phone onto somebody's fingertip, and have that coupled to an enhanced lens with a polarizing filter, you can actually see hemazoan crystals in the finger of somebody that is infected with Plasmodium falciparum and some of the other Plasmodia. So interesting potential for a cell phone diagnostic. It's a little kind of Star Trek-y, but super cool. I won't mention too much in the therapeutic space. That's the other piece of case management, is getting people on the right meds. Currently, we use a roster of 6 artemisinin combination therapies, which is artemisinin derivative plus a partner drug. They work, they're cheap, they're not going to work forever. Artemisinin resistance is already being detected in a couple different locations in sub-Saharan Africa. So the search is on for non-artemisinin based therapies, ideally single dose instead of 3-day therapies. Again, adherence issues. The most promising candidate right now is a combination drug, ganaplacide and lumefantrine, and there's 4 others in the pipeline that are showing pretty good promise. But yeah, expect new medicines for malaria soon. We'll go to the next slide and I'll talk a little bit about vector control. I mentioned earlier that VC tools, vector control tools, are really responsible for a lot of the burden reduction. So this is a huge area of interest, a lot of active discovery going on here. And some of it is just basic improvements to the existing tools that we have. So whether that's new insecticides to counter resistance or improving the durability of a bed net. So just doing what we, improving what we have now, big area of interest. But there's also some really cool kind of next generation stuff happening in the vector control space. One of those things, ATSBs, attractive targeted sugar baits. These rely on the fact that early in a mosquito's life cycle, it has to feed on sugar if it's going to mature. And it's only mature female mosquitoes that will bite and transmit anopheles. So if you can target a mosquito at the sugar feeding stage with a toxic sugar. These used to be called attractive toxic sugar baits. And then somebody was like, that's bad for branding. Let's change the toxic to targeted. If you have a sugar source with an oral toxin in it, you can wipe mosquitoes out before they ever mature to the point that they would be biting. So ATSBs, the current design that we're looking at, is basically a box. It's got a little membrane in it. The membrane is impregnated with sugar carrying these oral toxins. Mosquitoes will land on the membrane, feed on it, and die. It's basically a tool for reducing local mosquito population density. And what's cool is it gets at both indoor and outdoor biters as well. Amazing results from early field trials of these, cuts the population density of mosquitoes in a village or a region by over half, and even knocks down the entomological inoculation rate, how many bites you're getting a year, and potentially infectious bites knocks that down even further. Very cool tool, simple, small box with great potential. Insecticides, another area we're looking at here. These are basically 2-for-1 drugs that kill both parasites and insects at the same time. Ivermectin is the canonical example of an insecticide. And if you've ever given your pet heartworm medicine, it's ivermectin. So when you do a mass drug administration, an MDA, for deworming a population, you get this wonderful knock-on effect of killing mosquitoes. The challenge is that ivermectin in its current formulation doesn't last particularly long. It stays in the bloodstream for about 10 days. We need it to last in the blood for more than a month if we want to really knock down local mosquito populations. So there's 2 development pathways happening here. Ivermectin, we're looking at one slow release capsule and one injectable long-lasting ivermectin. And we're also looking at another class of drugs, something that would also be familiar to pet owners. Those are the isoxazolines, Bravecto, if you've ever given it to your pet for flea prevention, same drug. And we're looking at that as an alternative insecticide. And very quickly, the last thing I'll mention here, something you may have heard of, gene drive. This is basically CRISPR to introduce a deleterious mutation into a local mosquito population to specifically target individual species, just those handful of Anopheles mosquitoes that can transmit malaria, for example. So you basically release a batch of mosquitoes containing a gene drive construct. These are things that have been CRISPR'd into the genome, and the effector molecules can do everything from cause males to be sterile or impact a female's ability to either bite or lay eggs. And the notion is that this construct should spread locally. These things don't spread very far because mosquitoes don't fly very far, but it exquisitely targets just that particular species, just the one that's responsible for malaria transmission. So this is something, again, field trial stage. This is probably 10 years out from reality, but an exciting approach. If you flip to the next slide, I won't spend much time on this at all because I know I'm pretty much out of time, and this is really the last area I wanted to mention, but this is something I actually spoke about recently at the Women's Health Research Institute Symposium, and how much like the High Burden to High Impact Initiative is taking a new look at how we do malaria planning, thinking about gender gives us a new lens through which to consider our malaria planning work as well. So I will not mention anything in this area. I did cover it all in detail at WHRI, and I know I'm out of time, but if we start paying attention to the intersections of gender and malaria and improving women and girls' health outcomes, we get these wonderful knock-on effects where, you know, improving malaria will better the lives, the health, and the outcome of women and girls. Bettering the lives and health of women and girls, their education, their economic empowerment has knock-on effects on malaria too. So this is something we really need to start considering. So you can flip to the last slide, and I will just recap my takeaway message again off the top. I really believe we can achieve malaria eradication in our lifetime. This is one of the Zero Malaria campaigns, and that says in Swahili, zero malaria begins with me. It will take using the tools we have in a better, smarter way. It'll take new innovations like some of the ones we covered today. And I really hope that some of you have a role to play in that journey towards malaria eradication. So I'll stop there, and I think we've got about 6 minutes left for questions. Thank you all so much.
So Jen, thank you very much. It's Keish. Good talking to you. Yeah.
This was fun.
Yeah. And yeah, thank you very much, Jen. It's great. I'm going to be my best Bob Hancock here for you. Any questions from our STEAM audience?
I see one from Nancy in the chat.
I do see one from Nancy here. So it's a really long question.
Got a great preamble.
Nancy, do you want to Nancy, do you want to go ahead and maybe articulate that to Jen. Go for it.
I can miss that too.
Yeah, it's a fascinating talk. That's what most of the comment was. No. So you probably know about this. Michael Kramer, he's an economist from Harvard, developed a program, I think 15 years ago, called the Advanced Market Commitment. And it was it was basically guaranteeing a market for malaria vaccines and to promote R&D and access to the vaccines. And I think back then Gates Foundation supported it and several countries adopted it. Do you know if it's still in effect and if it's been effective? And in particular, the vaccines you spoke about, are they being developed under that program?
Yes, that is such a fantastic question. And not only has it been that individual program very successful, but it's basically expanded into an entire division at the Gates Foundation. So as I said off the top, the Gates is, it's very much an R&D focused organization. And they realized early on that, R&D is only as good as getting it out into the field. And you need things like market guarantees, like volume guarantees, in order to be able to kind of financially de-risk the development of these innovations, especially for smaller biotech firms. And really the COVID vaccine development process and the whole financial de-risking of that to accelerate development really underscored that, if you pay attention to market dynamics and give companies the freedom to explore without worrying that they're going to have to find a market for this and that they're never going to make their money back. When you remove those concerns, it greatly facilitates product development. So at the foundation, we've basically taken that lens and applied it to any product development that we do. So within our global development division, there's a huge group focused solely on market dynamics and market shaping. That same approach is in play at the Global Fund as well. They've got a huge team focused on market shaping. So for every new compound that's coming down the line, new diagnostics, we are relying routinely on things like volume guarantees and saying, yes, we will essentially fund the R&D for, company X, and we guarantee that, we've arranged that the Global Fund will purchase X of these commodities should they be ready. So it was wildly successful and has become a cornerstone of how we do things.
Fantastic. So it sounds like Michael Kramer deserved the Nobel Prize.
Yes. We love our health economists. We love our economists.
Thanks so much.
Other questions for Jen?
I know they covered everything in malaria. That was pretty much.
So Jen, I do have a question. As you know, what has happened with the pandemic over the last 2 years is there's been a reemergence of awareness of neglected diseases, emerging infectious diseases that kind of fell off the map, over the last few years and now have been brought back because of what's happened with COVID. So my question to you is, has there been some research in the last 2 years on surveillance of what's happening with malaria, with what's happening with COVID? Is there a commingling effect? Kind of like what's happened in India with black fungus and COVID. Any thoughts about that?
Yeah, great question. There doesn't seem to be any commingling in that way that we saw with the black fungus, but we know that whenever there's a health emergency or whenever there's a humanitarian disaster, cyclone, earthquake, you name it, malaria will always seize the opportunity and will surge. And in fact, in the West African Ebola outbreak, deaths from malaria outstripped the deaths from Ebola, just because the health system is so overwhelmed dealing with a crisis that it can't turn its attention to this thing that is just routinely prowling around looking for an opening. So I think what we did very early on, and we as the global malaria community, I think WHO, Global Fund, UNICEF, UNITAID, Gates, PMI, we all got around the table on a almost daily basis early in the pandemic to say, what can we do to ensure that access to essential malaria services aren't disrupted, that bed nets can be distributed as per usual, that case management isn't impacted too much. And we were worried. I mean, there was a moment where it looked like one of the major suppliers of RDTs was going to pivot their work entirely to focus on COVID RDTs and leave malaria completely in the dust. But thanks to sort of coordinated global action and figuring out ways to do campaigns safely, huge credit to Rollback Malaria, the RBM partnership, and the Alliance for Malaria Prevention in getting guidelines out on how to do a campaign safely in the time of early COVID. We didn't see the scale or the magnitude of disruptions that we feared. There was an impact. World Malaria Report does have a great write-up of how many excess deaths were likely attributable to the COVID pandemic happening at the time, but it certainly was nowhere near what we thought. So while there wasn't a commingling and sort of co-pathology, there was that opportunity for malaria to rear its head, which we seem to have quelled.
Okay, great. Yeah, that's really good to know. Other questions for them? Yes, yes, sir. I'm sorry, I don't get your name, but please go ahead.
Hi, Jennifer. How are
Hi,
you?
Morshed. How's
Yes,
it going?
sorry, Marsha. I
Yeah.
didn't see your. Yeah, go ahead.
Yeah,
Please.
nice to see you at least on Zoom. So I have a kind of easy question. Like you know that in most of the developing countries, although in developed country we go by the stages of the mosquito control, we try to do the larval control as much as we can before going to extreme fogging. But in most of the developing country, they start with fogging, and they don't give any notice or anything. So some of those agents are not very health friendly, and they are causing more harm than benefit in my view. So are you guys doing anything to prevent such thing and going through algorithmic approach like do the larval control first and do this and that, and then go to the last stage with the notification and everything to make sure that those countries will adhere the rules or something?
Yeah, no, it's a great question. And at the end of the day, it really depends on WHO guidance, and there's no strong guidance yet on larval source management. We know what's happening out there in the world, and MCPs are doing it. And it's a really good early, easy prevention tool, but it's something that's also kind of hard to do routinely, reliably, and sustainably. Bed nets are going to be second after that. Happily, you know, no detrimental health effects. IRS is third. There's always the search for better insecticides, and what I like about IRS as opposed to just straight up fogging is IRS, it impregnates the surface of the wall. So it's not really seeping out. It's not in the air like a fog is. Those fogging approaches are less common, I'd say. But yeah, you're always working towards a future where is there a better targeted vector control approach? And that's one of the things I think is really interesting about gene drive, the ability to just pluck a single species out of the local ecosystem and not have to worry about these broad spectrum, you know, carpet bombing type insecticides. Great question.
Thank you.
Other questions for Jen? I know Jen has to go in a minute or two, but now that we've got her here, we got to take advantage of it, guys. Anything else? Rich.
You can always hit me up on Twitter too.
Yeah.
That's okay.
Go ahead, Rich.
Yeah, no, that's okay. Wonderful as always. My question is so close to Morshed's too, just about vector control and the One Health approach of what is the effect on the planet of vector control too, and that often gets overlooked. And you know, we can solve one problem by causing another. And I'm sure the Gates Foundation, among others, are looking at that whenever we do a vector control type of thing. But yeah. Thanks for the fantastic overview. You can comment if you want to, but
no, it's great. I think one of the nice things you can think about too, you know, you want to do vector control in a way that has knock-on effects for good elsewhere too. So one of the simplest things to do is housing improvements. If the mosquitoes can't get in, that's really good vector control. And when you've improved houses, you're going to have knock-on effects for things like TB, fumes from indoor cooking. When you build a better housing structure, you get a lot of benefits. So thinking about housing as vector control is one of the angles we can take as well, and looking at it through the SDG lens.
I guess just to my counterpoint to that was actually more that mosquitoes are food for other animals.
Oh yeah.
and et cetera, et cetera. You know, we might also decrease bats because we decrease mosquitoes, but then, you know, and that might decrease COVID, but does that have some other negative environmental effects on the
world? So housing is a good example. You're just keeping the mosquitoes out. You're not taking them out of the population. You're just preventing them from biting people. So can you find those interventions that strike a balance of not damaging an ecosystem, but doing what they need to do, and perhaps even having these additional benefits like improved housing? Thumbs up.
Okay. Any final questions for Jen?
hit me up on Twitter at Jennifer Gardy. You can find me
And-
jennifer.gardy at Gates Foundation. I got to go off and vaccinate some foster dogs now.
One last thing, I do have a question
My
of.
brand.
You're talking
Yeah.
about, you were talking about ivermectin. Now, as you know, Jen, there's been a tremendous amount of negative press around my ivermectin for COVID and so on and so forth. I mean, what are your thoughts about all that? Making sure that that doesn't get all mixed up to what you're trying to do.
Yeah, no, that's a $1 million question there. It's funny in COVID, whether it was chloroquine or ivermectin, so many of the things in our malaria portfolio seem to get co-opted for benefits. I think the long-lasting insecticide work is still far enough out that by the time this actually came to market, ivermectin for COVID will hopefully be a long ago memory. It'll be a funny story we tell around the campfire.
Yeah, because that could be a problem for you, right? I mean,
active ingredients, upstream active ingredients for chloroquine. We were worried about, were we going to be able to get chloroquine derivatives for, or are we going to, some of the key pharmaceutical ingredients, if they weren't going to be available because people were so obsessed with, chloroquine for COVID, we were really concerned about that.
Yeah, for sure. Like the other drug that I was, that we were worried about is mebendazole, right? That's used a lot for pinworm and so on. And there's been concern that there might be some negative interactions on that one as well, just like ivermectin. So it's very interesting. Jen, we don't want to take up any more of your valuable time. We do want to thank you on behalf of NGDI. And I mean, you were one of the people that helped us get NGDI off and going back in the day. So thank you, Jen, so much. And good luck with your work at Gates. And you're in Chicago, correct? Is that?
I am, yeah.
Oh, yeah, the Windy City. It's a great place. So good luck, and I hope we get to see everybody face to face soon. And
I'll come visit soon.
Come visit. Thank you so much. So thank you very much, Jen, and all the best to you.
Thank you, Keish. Bye, all.
All right, take care, everyone. So I think we have our third speaker in a few minutes. I think she is still waiting to come in. And so I think we will take just about a 5-minute break, and then we will resume. So please do not leave because Dr. Amy Lee will be joining us in a moment. She's just getting off her duties at SFU and told us she'd be here right at the bottom of the hour. So it's always great to be a little bit ahead of schedule. So why don't we take a 5-minute break, and then we'll have Dr. Lester introduce Dr. Lee in about 5 minutes. So thank you, everybody, and please don't leave because I think you want to hear what Amy has to say. She's doing amazing work with sepsis in babies in Africa. So thank you very much, everyone. We'll just take a few-minute break. So colleagues, I believe that Dr. Lee has joined us, and so we'll get started in a minute or two. And hi, Amy Kishwasan, nice to meet you.
Hi, Kish. Sorry about running away. I was a host for MBB seminar, departmental.
No, we perfectly understand. We love the fact that you're willing to speak today, and thank you very much. Do you have your slides, or should we?
I do. I send it to Samia, but she mentioned that there might be some problem with the sharing.
Okay. So yeah, Samia, why don't you put them up, and we'll get started in about a minute. I gave everybody a 5-minute break, so and we'll start in a minute or so. So why don't we get the slides up, and then we'll get started. Okay. And all right, why don't we go ahead and get started? Rich, are you ready to go there, sir?
I certainly am, thanks. Just my coffee machine noise is winding down. Perfect, thank you.
And all right, well, our last session is about to start, so I'll turn it over to Dr. Richard Lester to introduce our speakers. So Rich, over to you, sir.
Right, great, thank you. And it's just my pleasure, in fact, to be able to introduce our final speaker of the day, Dr. Amy Leaf, who's an assistant professor in molecular biology and biochemistry in the department at Simon Fraser University. And it really taps off nicely and ties together some of the themes of our day. Neglected global diseases is initiative at UBC, as Keisha's alluded to. We decided, and they decided actually as co-founders, not just to focus on the neglected tropical diseases, which is a discrete group of 20 neglected diseases, but really those that actually affect impoverished people who have poor access to treatments and healthcare due to impoverished settings and otherwise. And the sepsis and malaria definitely falling into those themes. And we're particularly delighted to have Dr. Amy Lee, because she's also another working from British Columbia. And I think one of our UBC neglected global diseases to be part of a community and advocacy. And she's not only an outstanding scientist, she's a big advocate for work and access to medications. Her lab focuses on understanding of host immune responses during infection and neonatal sepsis, and how bacterial and other pathogens disseminate, and also identifying novel virulence and antimicrobial resistance genes. This particular talk I'm excited about because it ties together these themes of malaria, sepsis, children that have been going on today, and another one of our prominent researchers. So without further ado, I'll let Amy start and get to listen with the rest of you.
Yeah, thank you for that great introduction. And thank you for inviting me to sort of talk about some of our work on using systems biology approaches to understand neonatal sepsis in low middle income countries, and especially in Africa. Next slide, please. So the global disease burden study in 2017 basically showed that, about 20 million children less than 5 years old develop sepsis, and 2.9 million of those children die. And what's interesting when you dig deeper is that the risk of dying is really highest in the first month of life, also sort of known as the neonatal period. And when we look at the numbers, what we see is that neonatal deaths account for about 47% of the deaths that's seen in children under 5. And at the time, so I've actually started this work when I was a postdoc in Bob Hancock's lab. And so one of the first things that I did as a data scientist was basically to mine data from the UN interagency group for child mortality estimation, and kind of visualize where that neonatal mortality is happening. And so what I'm showing you is actually a heat map of neonatal mortality death per 1,000 birth, with lighter color being less death, obviously, and then the darker color with more death. And you can see really the biggest burden is in Africa and parts of Asia. So in today's talk, I will talk about sort of some of our current knowledge on neonatal sepsis. And I will also highlight a number of cohorts that we're studying. With the first study talking about the Gambia and the Papua New Guinea cohort, and the second study, the Malawi cohort. And I also just want to highlight, I'm a genomicist, a systems biologist. I do large data analysis, but really I'm just a tiny piece of this puzzle. I wouldn't be able to do the work that I'm doing without my clinical collaborators from around the world, and especially clinical collaborators locally at each of the sites that I've mentioned. Next slide, please. So what is neonatal sepsis? It's a life-threatening host response to a severe infection, and it can also be to trauma, but most of what we will be focusing on in this talk are to severe infection. And what we think is happening molecularly is that the bacterial, especially in the case of bacterial sepsis, that they have conserved molecular patterns called PAMPs that I'm just highlighting here, like LPS or lipoteichoic acids, that are recognized by monocytes via CD14 and toll-like receptor. And this recognition basically then lead to activation of a large number of pro-inflammatory cytokine, which then eventually lead to activating platelet activating factor, leukotrienes, and so on. And these molecular factors then basically changes the vasculature, and when the pro-inflammatory cytokine is not adequately regulated, this then effectively leads to a lot of vasculature damage that we see, which then eventually lead to tissue injury and organ failure. And so sepsis is effectively a systemic inflammatory response. And as I mentioned, it's mostly triggered by infection, and the outcome is then it leads to cardiovascular dysfunction and hyperthermia, microvascular thrombosis, leukocytosis, and so on, that eventually lead to death if we can't manage this. I won't get into too much details about some of the molecular work we're doing in trying to understand neonatal sepsis. Instead, what I will talk about are some of the larger omics studies that we're doing to try to gain further insight on a population level. Next slide, please. So what we know is that, as I mentioned earlier, young infants are really at the highest risk for sepsis. In high-income countries, this predominantly impact premature newborns, but in low-middle income countries, it's any newborn are at risk for sepsis. And it's particularly difficult to diagnose in infants, as especially early on in the disease process. And what's challenging to treat, without proper diagnosis is that in neonates, sepsis can also clinically progress very fast. We're talking about hours to mortality. And part of the reason why it's so hard to diagnose, especially in neonates, is that it's mimicked by many other conditions. And, you know, really regardless of whether or not you're in high income countries or low income countries, for bacterial sepsis specifically, the gold standard for diagnosis is still bacterial culturing, which can take up to 48 hours. So you can see part of the challenge when you cannot diagnose very rapidly and disease progress very quickly, it becomes a very challenging disease to treat. Now we know if we can provide prompt treatment, like with antibiotics, that really improves survival. However, we also know that, you know, with the challenge of antimicrobial resistance, when we overtreat and overprescribe antibiotics, that can also have major clinical consequences, not just on a population level, but also on an individual level. Next slide, please. So what I'm going to talk about today is basically how my lab, together with our clinical collaborators, have used systems biology to tackle this problem by first looking at what's happening in that first, during that neonatal period that makes the neonate so susceptible to infection, and effectively establish an immune baseline using systems biology. And then in the second part of my talk, I will show you some of our machine learning approaches to help with diagnosis of neonatal sepsis in low middle income countries, and how we think you know, using some of these molecular biomarkers can perhaps speed up diagnosis and prioritize treatment in cases where we know for certain that these are bacterial sepsis. And then what are some of our future directions in my lab, and some of the future questions that we're tackling. Next. Okay, so as I mentioned at the beginning of the talk, you know, the risk of dying is really highest in that first month of life. And if you look further, what you see is that, you know, 75% of that newborn death during that first month occur during that first week of life. So what makes that first week of life post-birth so unique, right? And, you know, when we started this study back in 2015, 2016, when I was a postdoc in Bob's group, you know, at that time, there were basically, there weren't any systems biology approaches to looking at first week of life. And there's actually a lot of technical challenges. Next slide, please. And so, you know, what ended up happening was actually Bob and a number of us, including Toby Coleman, who at the time was at BC Children's, and Beate Cutman, who is at Imperial and also at MRC Gambia, and Dr. Ofer Levy, who is the lead PI of this expanded program on immunization consortium, EPIC, that is a part of NIH-funded consortium, basically asked this question: can we use systems biology to help us understand what's going on during that first week of life? And can we then molecularly create this immune baseline for neonates that help us understand what's going on in healthy infants? Are we then able to you know, identify infants that are at risk for developing disease, and how does vaccination tweak that immune baseline. So as I mentioned earlier, this is a really large study with multiple sites, 2 clinical sites, one at Gambia and one at Papua New Guinea. And we have basically different cores that is responsible for each of the omic types. So for instance, transcriptomic was done in the Hancock lab. Proteomics was done in Boston Children's under Dr. Hanno Steen. And there's other clinical collaborator in Belgium who helped us figure out titers. And so this is a large consortium with collaboration across the world. Next slide, please. And the story really started with our clinical collaborators at Gambia, and Dr. Beate Koopman, who is the MRC lead at Gambia, basically helped us recruit a number of infants for our pilot study, as well as the full study, which I won't have time to talk about today. And, the reason why Gambia is such a great place for us to conduct this research is that it has a long track record in participating in clinical research and has made significant contribution to a number of vaccine development. And it also has one of the densest immunization schedule, EPI schedule in Africa, with a broad range of antigen. So when we started this study, we were able to basically tap into existing infrastructure at the MRC Gambia. Next slide, please. And working together with Dr. Koopman and Dr. Ijoko, we were able to create these community engagement events and again, tap into our clinical collaborators' expertise in their understanding of the local culture and basically recruit moms to enroll their infants in our study. And, as a mom with 2 kids, I think it's an amazing thing that Dr. Idoko and Dr. Koopman are able to do to convince a mom with a newborn to enroll their babies into our study. And it really highlights kind of the importance of, It really highlights the importance of having those local contact and the strength of our clinical collaborators. Okay, next slide, please. So this pilot cohort effectively is set up so that we have 30 infants, and they're split into groups of 10, with every infant having 2 blood draw in that first week of life. So the day of life 1 infant had their blood draw on both day of life 0 and day of life 1, and so on for the day of life, for the later day of life. And the idea of having that day of life 0 at birth sample is to create a baseline that we can then compare each baby back to their immune baseline at birth. And this study really took advantage of diverse expertise within the team, such that we were able to take from 1 ml of blood from an infant to do diverse omic characterization, and that included 200 microliter of blood designated for transcriptomics, and 300 microliter for plasma proteomics, and 400 microliter for basically single cell immunophenotyping. And so from this diverse group of experts, we effectively then generated multi-omics characterization that every infant had their transcriptome, their cell immunophenotype, their plasma proteome, plasma metabolome, as well as cytokine, just from that 1 ml of blood. Next slide, please. And what we observed that was very exciting at the time was by having that day of life 0 immune baseline, we saw this dramatic change across all omic, and I'm just showing you what happens in the transcriptome. And you can see this increase in differential expressed genes during that first week of life. And when you overlay that transcriptome onto a network, you can see increase in network complexity over that first week of life. And what these functional pathways that are changing during that first week of life are things related to immune responses like interferon pathways, as well as cellular responses to stress. And so this is quite amazing finding at the time, as this dynamic nature during that first week of life in a newborn has never been seen at that time. And it's very different from what we know of adults. If you take my transcriptome from day 1 of the week versus day 7 of the week, there's actually not a lot of changes that occur, right? So this dynamic gene expression changes in neonates is one of the novel findings from this study. And we see this dynamic change in all molecular space that we looked at. So proteome, metabolome, cytokine, and so on. So next slide, please. So due to time constraint, I'm not really going to go into the methods, but I'm happy to talk about this. Effectively, while I was in Bob's group, working together with Casey Shannon and Scott Tebbett, we then developed a number of multi-omic integration tools. And what we found, next slide. Next slide, please. What we found was that when you integrate all these different molecular space and data from these different omic characterization, you actually find consistent information that in a neonate during that first week of life, we see consistent change in important pathways like neutrophil degranulation and platelet activation, and various interleukin pathways. And this consistent change that is critical during that first week of life, next slide, is actually then also conserved in a different independent cohort, the Papua New Guinea cohort, where you can see what this is showing you is that infants that are day of life 0 with the ellipsoid built using the first cohort, the Gambia cohort, and the dots indicating the Papua New Guinea infants actually show significant congruence across different ohm. And that when you look at specific molecular markers that you might be interested in, there's that consistent change regardless of whether or not you're an infant from Gambia or from Papua New Guinea. And this consistent change and considerable overlap in all the different ohm that we've looked at, again, highlights the importance of pathways like interferon signaling, complement, neutrophil activity. And so with this understanding of immune baseline that's going on in the first week of life, sorry, next slide, please. What that tells us is that, neonates, at least across these two divergent cohorts, show there's a dynamic immune development trajectory that is highly conserved, and it's very consistent across different omics. And, our previous assumption that susceptibility to infection during that neonatal period is due to immaturity may need to be revised, because potentially why neonates might be susceptible to infection could be due to adaptation to the demands that's placed on the immune system during early life. And with this immune baseline, we can maybe then use this to help us identify at-risk individuals prior to disease onset that can help us guide reestablishing the homeostasis once that immune baseline is perturbed. And what happens when we overlay vaccine on top of that? And so these are some of the bigger questions that the larger study that's currently ongoing is focusing on. Next slide, please. So with the remaining time, what I will talk about is our second study where we're using large omics to help us identify bacterial sepsis biomarkers that can perhaps aid in diagnosis. And as you heard earlier on, that diagnosis is challenging given that you required blood culture, and disease progression can happen very fast, right? And, as you've seen, that neonatal sepsis really has the highest burden in low middle income country, especially in Africa. So, one rationale that we have is that by identifying molecular markers that can help us identify those infants suffering from bacterial sepsis, then perhaps we can deliver appropriate treatment much faster. Next slide, please. And our current study, and this is work that's ongoing, so I'm only going to show a limited subset of our current data, but our current analysis design is to effectively identify biomarkers that can identify infants that are suffering from severe disease versus infants that are suffering from bacterial infection. And the reason why we want these markers that can separate out disease severity from bacterial infection is with the bacterial infection, the appropriate treatment would be antibiotic therapy, whereas with disease severity, perhaps other type of treatments would be more appropriate. Next slide, please. And so this study is done in collaboration with Dr. Lavoie and Dr. Papaso at BC Children's and their clinical partners in Malawi. And effectively, our goal is to, first of all, develop whole blood transcriptome markers that will allow us to identify those infants at risk for bacterial sepsis. And these biomarkers that will also give us more insights into the epidemiology of neonatal sepsis in terms of understanding the incidence, the severity, and the risk factors for mortality. And Malawi is one of the poorest country in Africa with really low life expectancy. This, when we started this study back in 2018, sorry, next slide, please. basically, Dr. Papasul and Dr. Lavoie started recruiting back in 2018. And this is a case control study where infants that showed up at the hospital with suspicion of sepsis, showing clinical signs of sepsis, have their bacterial culture or blood culture taken. And out of the total number of infants that we have about 20% with positive bacterial cultures. We also have control infants that are non-septic and they're admitted at the hospital for non-sepsis, but they do not receive antibiotics. But one challenge with this study is that because we have contamination in our gold standard, one major issues that we've been working on bioinformatically is to try to understand what would be considered as gold standard when we're then developing our biomarkers. And so working together with Dr. Lavoie and Dr. Goldfarb, what we ended up doing was for all of the blood culture and one sample of cerebrospinal fluid culture, we then actually run basically mass spec to, as well as doing genome sequencing in my lab to ensure that we have pathogen characterization and classify infants as culture proven bacterial sepsis if they have known pathogens, while those ones that are not commonly considered as pathogens, such as coagulous negative staph and so on, these infants will be grouped in the contaminant group. Next slide, please. And so with this cohort of 401 enrolled infants plus 51 control infants, these are all full-term infants. We effectively have two groups with the septic infants having culture positive samples, control infants without culture positivity, and also a clinical septic infants that have culture negative, but RNA-seq data collected. Okay, next, please. And so using that data set, we basically ask, how do we define bacterial sepsis? And can we just simply use their transcriptome to separate out these infants? And to do that, we use a machine learning approach where we apply supervised machine learning using SBI-CA on the infant blood transcriptome. And the labels are basically using the definition that I showed earlier, where we have the bacterial culture as well as clinical observation. And what you can see is that using transcriptome and machine learning label, we can actually clearly separate out infants that are admitted for non-septic reasons, which are labeled orange, infants that have sepsis, which are labeled gray, as well as these infants who have contaminant bacterial culture, but show clinical sign. Next slide, please. We then go on to further classify to identify molecular markers that can help us separate out those infants with bacterial sepsis from healthy control. And what I'm showing you here is a heat map with the rows representing the genes that's picked out by our machine learning model. And the orange in this row indicates infants that have sepsis. And what you can see is that our markers in general is pretty good at separating out septic infants from the control infants, which is indicated as gray here. And we're working on refining this marker further so that we can classify some of these infants that are grouping with the healthy controls better. Next slide, please. Now, I also mentioned our other goal is to identify those infants that have severe disease outcome in the sense that they go on, they die. And so here, what these markers are showing you is that we can actually group infants that have more severe outcome on the left versus infants that have less severe outcome, and basically infants that have sepsis but do not die from sepsis. And similarly, we're working on refining these markers so that we can reduce our misclassification rate. Next slide, please. So in summary, what we see is that our molecular markers support a high rate of bacterial sepsis in this cohort. And, you know, while transcriptome signatures can be attributed to disease severity, what we've seen now is that we actually have different sets of markers that can separate out infants that are have very severe disease versus infants that just have bacterial sepsis. And having this this signature that can identify infants that just have bacterial sepsis will allow us to minimize some of the overuse of antibiotics. And it can potentially help us understand some of the immune mechanistic differences, as well as go back to our cohort to classify some of these infants that have negative blood culture, but are showing very ill clinical symptoms. Okay, next slide, please. So some of the current work that's happening right now is that we, in the larger cohort study from Gambia, we have 720 infants, and we've been able to take their at birth sample before they develop sepsis and develop a set of biomarkers that predict whether or not those infants will go on to develop sepsis. And what I'm showing you here is the non-sepsis are brown with the sepsis in orange. And you can see that the time of disease occurrence is showing in shape. And so currently we're looking at, you know, what these biomarkers mean and functionally what these biomarkers are doing. And this is some of the animal models that will help us define these molecular mechanisms. And with that, I think I'm just going to jump to the acknowledgement slide. Sorry, can we jump? Yeah, there we go. So I just want to thank all of my collaborators who've done all the hard work of collecting samples. In the first study, as I mentioned, these are largely done as a part of the EPIC HIPSI consortium that's based out of Boston Children. And in the second study, the Malawi study, it's led by Dr. Lava and Dr. Papaso at BC Children's. And with that, I'm happy to take questions.
Okay, thank you very much, Amy. That's fantastic. So open up for questions for Dr. Lee. So Amy, I have a question. This might be a little off, but for your work down the line, I did notice that for your assays and for your markers, you're using blood
Hmm.
And I guess one of the bigger issues is from a practical perspective, that's quite invasive. Is there any thought about doing work where you'll be able to do some of these markers using saliva tests or something like that? What are your thoughts about that?
Oh yeah, that's really interesting. So I think Dr. Jane Hill at UBC is looking at ways to detect infection using breath. So that, that's definitely an approach to look into, because I think it's pretty challenging to get blood, and especially from a sick neonate. We were able to do it with 1 ml, but it's still venous draw. So it's, like you said, it is very, very invasive. I think, unfortunately, right now we're predominantly focused on blood, because I think a lot of the omics toolkits are really well characterized. And
no, from an omics perspective, I think you're doing exactly the right thing. And for blood, that's why I don't think my question's a fair question to you at this point. But I was just thinking ahead down the road from a practical perspective, because I think what you're doing is extremely important and will be an important tool for us. But the practicality will be getting, a sample from an invasive, doing an invasive approach could be a problem. So being able to get it from a non-invasive way, like saliva or something like that would be awesome. But I'm sure there's huge technical challenges with that.
Yeah, for sure.
Yeah, for sure. Rich, I think you had a question. Sorry, I interrupted you. Rich was going to do the Q&A. I'm just excited by your research. Sorry, Rich, go ahead.
No problem at all. And I want to make sure I'm not dominating the question. So those of you, please either raise your hand or just speak up on there, because we really wanted, this is an amazing opportunity for you to talk directly to our speakers. I can never help myself having a lot of.
I think we have a question for Motion again. So go ahead, sir.
Recently that I saw this product, and looks like it's FDA approved, and they claim they can do those neonatal sepsis and all sorts of sepsis within an hour, very accurately and specifically. And I kind of put the website on the chat box. So my question that, do you know anyone, you have any experience with this? And if there is good or bad, is a commercial product looks like, and they're doing big marketing.
Yeah, so I don't actually know Septicite. I'll take a look. So one thing that I will note is that a lot of the markers, and I didn't do a good job in my intro to kind of lay out. So part of the problem is with a lot of the markers are typically done with adults. And my lab collaborates still quite closely with Bob's group. And what we're finding, at least in the Malawi cohort, the markers are different between adults and neonates. So, it really depends on what people are doing when they're developing those markers. And, I feel like neonates are also tend to be neglected quite a bit in a lot of the research, in part because it's so hard, as Kish mentioned, it's so hard to get enough blood to do some of these work, right? And then, so the other point I just want to highlight is that in low middle income countries, what we're seeing, the infants who are susceptible to neonatal sepsis, really we see it in full term infants, right? Whereas in high income countries, it's really prematurity and preterm infants who are at risk for sepsis. And actually what we know from my work collaborating with Andrew Curry in Australia and Sherry Ann Ng is that preterm infants actually have a different immune development and immune trajectory compared to full-term infants, right? So that there's also potentially differences in what those markers could be.
Thank you.
Okay, Rich, go ahead.
Yeah, I will ask my question. A really important, fascinating talk. And what I was struck most by, I think it was when your second study on the omics, the rapid evolution of the omics in the first week of life, and the concept of a genetic component and an adaptive component. And I guess the genetic component really starts at conception. And then thereafter, there's an adaptive environmental stimulus. And you mentioned the PAMPs, or the pathogen-associated molecular patterns. So in that omics, and I'm not sure if I caught it, do you have preterm? I'm imagining it's mostly sterile environment, but the moment you're born, pass through, you're exposed to the outside world and all of its wonders and all of its pathogens, and also normal commensals and healthy stimulation as well. So I think that's just such a tremendously important area of work that might set someone on a life path of differential susceptibility to health conditions and infections forward. So in that work, number one, what is the contribution of the microbiome that someone is exposed to in that really, really early term that might affect their adaptive omics, as well as maybe other things, temperature, sunshine, there could be a number of things. Thanks.
Yeah, for sure. So these are actually questions that we're now investigating. So we have, so the pilot study, I don't believe we have the microbiome data for it, but for the larger study that's a part of the vaccine study, that study, we basically have fecal microbiome taken at at their birth, and then also at a later time. What I will mention that's sort of interesting, that kind of plays into your, indirectly maybe answers your question, is that in the neonates from Papua New Guinea, we can actually detect mothers who chew batel leaf from the infant metabolome, because it shows signature of someone who has been exposed to tobacco, basically. And so it's quite interesting, some of these additional confounding variables that we're collecting, right? So including breastfeeding, looking at whether or not a baby is born during the wet season versus the dry season, right? Because potentially there might be nutritional differences. And so these are all larger studies that larger questions that we can definitely ask with these studies.
Yeah, thank you. It reminds me somewhat of some of our other colleagues in the city and around here regarding early life exposure to certain pathogens might actually make you more susceptible long-term to asthma and other things. So the direct effect on the ongoing adaptive immune system is fascinating. Thank you very much.
So I think we need to wrap things up. So Amy, thank you so much for participating and giving an outstanding talk. And I think there are people that I will probably reach out to you, and we'll let NGDI be your facilitator. And we'll, if they have questions, we'll pass them on to you, and
Sounds great.
So thank you so much, and good luck with your future work. And I do think I loved your comment about that neonatals are neglected. We have this definition of neglected diseases, but I have to say that anything that's neglected really comes under our umbrella. So I think you're absolutely right about that. So congratulations on your work, and good luck with your future studies. And it'll be interesting to see as you progress, for sure.
Thank you.
And so, colleagues, we're going to wrap it up and finish. I think that Rich and I would like to thank everybody for your attendance. And again, it's part of our NGDI series of highlighting some of the great research that is going on in neglected diseases. And we'll probably be having we will have another symposium in the fall And Rich and I are hoping that this one will be face-to-face, and I hope you will attend. So look toward those. Again, look at our website. You'll be seeing new content on there and new things. We have a very active Twitter feed at NGDI UBC1. Please check out our Twitter feed, and we've always got up-to-date information about what's happening in the world of neglected diseases, as well as the great research that we're doing in the community. So thank you very much. And Sammy has just put into the chat the website. And like I mentioned in the beginning, we've got a lot of new activities at NGDI. We're doing a PR fundraising campaign starting hopefully in April. We're working toward that. We've got a new student award that we're hoping to adjudicate in the fall, and we're doing terms around that award over the summer with our advisory board. We've got our advisory board that has been refreshed, and we're looking to have some additional activities coming up in the fall. So NGDI is out there in a real way, and I want to thank all the advisory board members, and particularly Rich for his leadership and all the hard work that he's done, as well as Nancy Galini, Bob Hancock, Kathryn Fuse, Rachel Fernandez, who is our Associate VP of Research. She's been outstanding, and everyone else, David Patrick, as well, for supporting NGDI. Any last comments, Rich, before we close for the session?
No, just that. Thanks again. And I'll say for those, anyone who has recommendations, this is really about networking. What drew me to NGDI when Kish and Bob started it was the advocacy and networking that goes on here. So if you have people to recommend that you think we should consider for future symposiums, speakers, etc., please bring them forward. Also, students, again, if you have opportunities, things you want to get involved with, reach out to us as well. And we look forward to hearing from you all. Thank you.
Yeah, absolutely. Thank you. Thank you for saying that, Rich. And in fact, we'll probably do some kind of wine and cheese event and event in the fall, as we all start to open up again and hopefully get back to some semblance of normal life. Then we'll hopefully see each other face to face. So thank you very much.
I just want to thank Fanan and Samia for the
Absolutely. I was going to say that, but I'll let you do that. Yeah. Fanan and Sammy have been outstanding. Thank you to both of you for the hundreds of emails back and forth that we do, and for everything. You both have been fantastic, and we certainly could not have done it without both your help. So yes, thank you, Rich, and thank you, Sammy and Fanan, for everything that you've done. And so on. So thank you, everybody, and have a great rest of your day and weekend. And we'll be talking to you soon. Take care, everyone.
Thanks.